Precalculus, Chapter 1, Section 2, Functions and their Graphs. This is part 2 of the notes. We're going to go through quite a few things. We're going to talk about relations, which is just, in math, it's where we have a relationship of one variable to another. We're also going to talk about functions, whether a relation is a function. We're going to talk about if an equation can be classified as a function. And we're going to evaluate functions. We're going to graph functions by plotting points. We're going to talk about, from the graph, how to identify functions using the vertical line test. We're going to look at obtaining other information about functions from their graph, how to identify domain and range of a function from its graph, and finally, how to identify the intercepts from a function's graph. So let's start by defining a relation. Get this definition down if you need to. A relation is a set of ordered pairs in math, one thing to another. The set of all the first components of these pairs is called the domain, and the set of the second components is called the range. You can also think of the set of the domain values as the inputs, and the set of the range values as the outputs. So let's look at this relation and let's find the domain and the range. So let's start with the domain. So this is a collection of ordered pairs, so we're going to look at the first element of each pair. So that would be 0, 10, 20, 30, and 40. So this is our domain. It's the set of all the first elements or the inputs. Now the range is the set of the second elements or the outputs, 9.1, 6.7, 10.7, 13.2, and 21.2. Notice we write the domain and range as a set and we use the set braces. Let's talk about a function now. So a function is a correspondence from a first set called the domain to a second set called the range, such that each element in the domain corresponds to exactly one element in the range. So that means in the relation to be a function, the x's cannot repeat, and for each x, there is only exactly one y. There cannot be two y values. So let's look at this relation. It's a collection of ordered pairs. I'm going to focus on the first elements or the inputs to make sure that I don't see any inputs that are repeated. And I don't. And then, so that means that each of these non-repeated inputs has a separate output. So this collection, this relation, collection of ordered pairs is a function because for each of the input values, there is exactly one output value. Now, functions as an equation. So if an equation is solved for y, and more than one value of y can be obtained for a single x, then the equation would not fit the definition of a function. So let's work an example. Here in example 3, we have the equation x squared plus y squared equals 1. So let's solve for y and see what we get. We'll subtract our x squared over. Then, to work backwards from y squared, we have to take the square root. When we take the square root, we acknowledge that there can be both a positive and a negative square root. So we put the plus or minus sign. What that means is that there are two possible values for y. So for example, if I let x equal 0 and plug that into my equation, I will actually get two answers, positive and negative 1. So that means this equation does not classify as a function because for this x value, there are two y's that go with it, two outputs. Function notation. So there's special notation that f and parentheses x, and we read it as f of x. It represents the value of the function at the number x. So set fully, we have the function f in terms of x. But we don't want to say that every time. That's rather long. So then we just do a little shortened version of that, and we say f of x. So when you see the f and the x in the parentheses, you read that as f of x. And what you're saying is the function f in terms of x. All right, so in example 4, I believe it is, f of x equals x squared minus 2x plus 7. We're going to evaluate f of negative 5. So that means for all our input x's, we're going to plug in negative 5. So we'll have negative 5 squared minus 2 times negative 5 plus 7. So working left to right, we have 25 plus 10 plus 7. 35 plus 7 is 42. And then I'm going to bring down that function notation to show that f of negative 5 equals 42. Function notation is nice because it's descriptive. I can tell in a glance that when I plug in negative 5 into this function, I get positive 42. When you graph a relation, you can tell from the graph if it's a function. So by doing what's called the vertical line test. So if any vertical line intersects a graph in more than one point, then the graph is not a function. And that's because when that vertical line touches the graph or the curve more than once, that indicates more than one y value for a single x or for a single input. So let's look at some examples. Look at these graphs. So I'm going to draw a straight line as I'm able to on each of them, and I'm going to draw multiple vertical lines through most of the graph. So you can see that no matter where I draw my vertical lines in this first graph, they will only intersect once. So yes, this is a function. For each value of x, there's one y. Now this one, I right away can see that my vertical line is intersecting more than one time and multiple parts of the graph. So that means for our x values, there are multiple values of y. So that means that this is not a function. It's a relation, but it's not a function. So this graph, yes, it passes the vertical line test. It's a function. This one, a circle. Circle is not a function because for values of x, there are often two y values, two outputs. Now take a look at this graph. This is a real life situation. So this is T cell counts and HIV infections. So it's comparing time after the infection in years to average T cell counts, and it is per milliliter of blood. So this says find f of 5. So that means we're going to look along the x-axis for 5. And then I move my eyes until I see where it intersects the graph. And then I look over and I see that's where my y value is 400. What does this mean in terms of the graph? So this means after 5 years of infection, there's a T cell count of 400 cells per milliliter. Now we can look at outputs and find the inputs. So f of x equals 100. So what value of x on this graph is 100? So I'm going to look on the curve and see where it's at 100, and it looks like about after 9 years. You would have a T cell count of 100 per milliliter of blood. Let's identify or talk about identifying the domain and range from a function's graph. So to find the domain of a function from its graph, you're going to look for all the inputs on the x-axis that correspond to points on the graph or the curve of the line. To find the range, you're going to look at all the outputs. So how I do this is for the domain, I run my eyes left to right along the x-axis. And then I'm looking above and below to see where, in this case, it's a line. So I notice that above negative 2, that's where the line starts, and below positive 1, that's where it ends. I also notice that line has an open circle, so I'm not going to include -2, and I'm actually not going to go up to 2. It just goes to 1. Now for the range, I'm going to put my eyes along the y-axis. I'm going to start and move upward and looking left or right to see where the line shows up. So the line starts across from where y is -1 and it ends across from where y is 2. And it is equal to -1, but I have an open circle across where y is 2. So we will not include 2 in our range. To identify the x or any or y intercepts from a function's graph, you're going to look at the points at which the graph crosses the x-axis and then look at the points at which it crosses the y-axis. A function can have more than one x-intercept, but not more than one y-intercept. Then it would not be a function. So read the graph left to right, and first let's look for the x-intercepts. So where it's crossing the x-axis, and we'll write this as points, as ordered pairs. So it's at -3, 0, -1, 0, and 2, 0. Now put your eyes along the y-axis and find that one y-intercept, and that's at the point 0, -6. All right, this concludes the notes over Chapter 1, Section 2, Functions and their Graphs.